Hey, welcome back. This is now 9.8 on power series. So we have started connecting the dots between functions and series. It will turn out that the polynomials we introduced in the last section, all we have to do is kind of extend those infinitely, and we'll end up with our representations for the functions. We'll call those things Maclaurin and Taylor series eventually. But right now we kind of just speak in generalities about these objects, and we give them the name power series. And you can intuitively kind of think of them as just as infinitely long polynomials. We'll go ahead and define these things right here. So it's basically just a series, but with a variable popped in there, and such that the variable has the behavior of working kind of like a polynomial. It has, increasing exponent. So a sub 1 x. And if I just stopped right there, right, it would just be a Taylor, or rather a Maclaurin polynomial degree 1. And then here's a Maclaurin polynomial degree 2, right? Etc. But this thing goes on and on forever, right? We just want to study these things in their own right, and it'll take until 9.10 to really make the connection between the Maclaurin polynomials and the Maclaurin series. But we're just going to take this side road for a couple minutes here in 9.8 and study these things independently. How are we going to study them? Well, we're really interested in their intervals of convergence. So basically just where are they going to be useful? So we'll get these big, long, infinitely long polynomials, which represent functions, but they won't work for all x values, right? They'll only work in certain intervals. So what we do in this section is sort of figure out how to find those intervals of convergence. And it's kind of just what you're doing with your numerical series in 9.2 to 9.6, but on steroids, right? Because we're introducing this variable. And rather than finding whether it's convergent or divergent just at one point, we're finding convergence and divergence for what values of x. Right? So maybe before, what was going on, where we're trying to figure out whether or not the series of 1 all over x to the 3 to the n converged or diverged. Right? And we know that this thing is geometric. The r value is 1/3, so the absolute value of that is definitely less than 1, and therefore it's convergent. Okay, now we want to take it up a notch and find the interval of convergence if we kind of replace that 1/3 with just a generic x. Okay. Now we need to consider an interval of convergence. And you don't have to worry about, well, maybe it'll converge out there at 1/3 and not converge there at 2, and maybe it'll converge at 5 and then not converge at 7. No, it'll turn out that it'll be an interval, or it'll be everywhere, or it'll be nowhere. Okay, well, with the exception of the center. It's always going to converge at its center. Okay, so the case is that we are going to have, well, first, it'll converge only at its center. So basically in these things, if you plug 0 in, or if you plug c in, it's just going to equal 0. The second case is the awesome case where it converges everywhere, so it's very useful. And then the third case, it'll maybe just be some kind of bummer interval. Okay, so c, and in this third case, it's really a bummer because you got to go back and check the endpoints for convergence. So you must separately, so it means more work, separately check endpoints for convergence. Okay, great. The workhorse for us is going to be the ratio test, which is awesome because that's my favorite test. The bummer part, again, is if you get one of these intervals of convergence, then it's going to be a matter of using the test from 9.2 and the 9.6. Okay, so anyways, let's remind ourselves of the ratio test. We are going to produce this limit, which is the ratio of the a sub n plus first expression divided by the a sub n expression. And then depending on that value, so first, if rho is less than 1, it's absolutely convergent. 2, if rho is greater than 1 or rho equals infinity, then it's divergent. And then thirdly, if rho is equal to 1, which is what happens at the endpoints of intervals, then it's inconclusive and you have to go to the other tests. Okie dokie. So let's look at number 3 in the homework. You have the sum from n equals 0 to infinity of x to the 3n all over 3n factorial. Okay, great. So here now I need to worry about the absolute value symbols. Before I could kind of throw those in the trash when I was just dealing maybe with a series of all positive terms. But because we have this variable here, this x variable, it's not going to be the case anymore. So here I am getting a sub n plus 1. So wherever I see n, I'm replacing it with n plus 1. And then it will be divided by a sub n. Let's just multiply by the reciprocal. We could collect common terms and kind of simplify a little bit. 3n factorial, if you'd like, you can start, go ahead and, write it out. Be a little careful. I don't know why people make this mistake. So people will like to write 3n plus 1, but it's not, right? You have to distribute. It's 3n plus 3 factorial. And then we could write it out. Write out enough terms so you can see a cancellation happening. There it is. Okay. So this junk will cancel with that junk. Sorry. And then you'll get an x cubed in the leading term there. X to the 3n plus 3 minus 3n is just x to the third. So I have the limit of the absolute value of x cubed times 1 all over 3n plus 3 times 3n plus 2. You could factor out the x cubed, but you gotta be a little careful to take those absolute value symbols with you, because the x cubed is not dependent on n. Remember, this limit is n going to infinity, okay? But it's not dependent on n, so you can factor it out of the limit, and then we don't need the absolute values anymore. 3n plus 3 times 3n plus 2. And so what are you going to get? Well, this limit is going to go to 0, so it's just going to be x cubed times 0. And for any value of x, what does that equal? Well, any number times 0 is just 0, so this equals 0. In other words, your rho value is equal to 0, okay? And that works for any x. So we have what? For any x, rho equals 0, thus the power series is convergent for all x. Okay, so that's going to be the, from above here, the second case, r equals infinity. Okay, so it's basically saying the radius of convergence is equal to infinity, but the interval of convergence, so this r equals infinity is the radius of convergence. But the interval of convergence, I'll just write IOC for interval of convergence. That's going to be negative infinity to infinity. It's just all real numbers. That radius thing's a little bit weird. So you can think of like r equal infinity means like from 0 to infinity. Okay, that's like they kind of split the number line into two parts. So I'll talk more about that in a second. Let's look at another one. So we want to look at one of each case, obviously. Let's look at number 8. So I have the sum of 2n factorial times x over 6 to the n. And I'm going from n equals 0 to infinity. And then I'm going to get my row value. So that'll be the limit of the absolute value of, replace n with n plus 1. Whoops, I'm carried away there. So we have x over 6 to the n plus 1 is what I'm trying to write. That'll be all over 2n, a sub n. So I don't have to multiply by reciprocals this time. It's going to be simple enough. So again, so again, 2 times n plus 1 is not 2n plus 1. It's 2n plus 2 factorial. Okay. So I'm going to start by expanding that a bit. 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, blah, blah, blah. 2 times 1 times x all over 6 to the n plus 1 all over 2n factorial, which is 2n times 2n minus 1. I can see the cancellation. 3 times 2 times 1 times x over 6 to the n. Okay, so the 2n factorial parts are gone. I'm going to have the limit, the absolute value of 2n plus 2 times x over 6 to the n plus 1 over x to the over 6 to the n will be x over 6 to the n plus 1 minus n, which is just x over 6 to the first. You can factor that x over 6 out. You get the absolute value of x over 6 times the limit of 2n plus 2. And that limit of 2n plus 2 is going to go to infinity, right? And that will be infinity for all values of x except one of them. So the one that won't work is the center value. Okay, so that's the first case that we have. So we already solved case 2. This is case 1, where C is the center. And in this case, the center is 0. So the limit will converge. This row value will equal 0, which is less than 1. Therefore, it'll be absolutely convergent at 0. But otherwise, it'll be infinity. And our ratio test says when it's infinity, it's divergent. So for all x values except 0, the series will diverge. Okay. And in that case, the radius of convergence is just going to be that value where it's converging. So r equals 0. Okay. So 2 cases down. We still want to look at this third case now, which is the long case. And you see this, it's kind of a bad day, right? But anyways, let's see at number 5. I have the sum of 3x to the n from n equals 0 to infinity. So go after my row value. Row will be the limit of the absolute value of the ratio 3x to the n plus 1 all over 3x to the n. And that will be the limit of the absolute value of 3x. And then you can factor out the absolute value of 3x. And you just have the limit of 1. Limit of 1 is 1, so you end up with 3x. Okay, so the ratio test says if that expression is less than 1, it's absolutely convergent. So what you do is take that expression, this absolute value of 3x, which is the same as 3 absolute value x, and say it's going to be, or the series will be absolutely convergent when this thing is less than 1. In other words, expanding it, well, first I'm going to divide both sides by 3, and then I could expand it. It'll be absolutely convergent in that interval. Okay. The radius here, this is what I was talking about above, where you kind of split it in half. If you look on the number line, here's negative 1/3, right? And then 1/3 is over here. The radius is just half that interval. So you can almost imagine that it's really the number line is sitting there on, going through this circle. So the radius is half the diameter, right? So the radius value from this is just going to be 1/3. So that's kind of the weird thing about this radius value. Honestly, I think they just get rid of it and say the interval of convergence. Just deal with that. This is silly. Maybe it has something to do with higher dimensions. Like if I had my PhD, I would understand. But anyways, for the homework, you need to know the radius is 1/3. The interval of convergence is troublesome, right? Because at those endpoints, negative 1/3 and 1/3, that's going to be basically where this thing equals 1. And we know from the ratio test that's trouble. Rho is 1, that's inconclusive. Okay, so what we need to do then is to go and check those two endpoints, and this is the bummer. Okay, so you need to, we will need to check x equals negative 1/3 and x equals positive 1/3. And then this will just turn into a 9.2 to 9.6 problem. You're plugging these numerical values back into our summation. Let's remind ourselves the sum was this. 3x to the n, sorry. Right. So we're going to try x equals negative 1/3. And wherever you see an x in the power series, you're replacing it with a negative 1/3. Okay, and then you got to use your rules of exponents and stuff to simplify, rules of algebra or arithmetic. This will be negative 1 to the n. And this is geometric, right? Or you could do, if you want to, you could do nth term test. So note nth term test for divergence. That's usually where you want to start when you're working with these tests, is to do an nth term test. And I had the limit of negative 1 to the n, which does not exist. Of course, that does not equal 0. So by the nth term test, it's divergence. It's divergent. So at that endpoint, it's divergent. And when you go to write out your interval of convergence, when it's divergent, you'll put an open parentheses, so you're not including that point in your interval of absolute convergence. If it was convergent, you would put a closed bracket on it like that, okay, on the side that's convergent. So if we found that negative 1/3 was convergent, we would have put a bracket there, right, like that. I don't know what's going to happen on the other side. But we found it was divergent, so we have to put a parentheses. Okay, then we'll go and check the other endpoint and see either I'm going to put a bracket if it's convergent or an open parentheses if it's divergent. So the other endpoint I got to check. And this time I'll have 3 times 1/3 to the n, which will just be the series 1 to the n, which is just 1. And I could do the nth term test again. So again, I'll take the limit of the terms of the series. The limit of 1 is just 1, which is not equal to 0. Hence, it's divergent over here, too. There's no real pattern to the divergence and convergence. So if one side is convergent, it's not necessarily going to imply that the other side is convergent. Okay. So unfortunately, you won't be able to pull that kind of trick. Okay. Let's look at number 12. Or actually, well, I want to give you a quiz here. Yeah, let's make this, well, no. We'll make the quiz you checking for convergence on the endpoints. Okay, so number 12, we have the series n equals 0 to infinity of -1 to the n times x to the 2n plus 1 all over 2n plus 1. Okay, so I got to get my rho value. And so I'm going to do the limit of the absolute value of, and now I got to put 2n plus, let's make this part the video quiz. Okay, so it's a fill in the blank here. So this should be, the first term is a sub n plus 1, and then I'm going to multiply by the reciprocal of a sub n. And you just need to fill in the blanks, the tops and bottoms of both of those fractions. Once you evaluate that, it'll equal x squared limit of the absolute value of 2n plus 1 all over 2n plus 3. And then the limit of 2n plus 1 over 2n plus 3, you could just circle the high degree terms in the numerator and denominator. It'll be 2 over 2. Limit of 2 over 2 is the same as limit of 1. Limit of 1 is 1. So you end up with x squared. Okay? So real easy quiz this time. You just have to fill in those blanks. Let me pause the video. One thing that I shouldn't see is a -1. Okay, so you're not putting in -1 to the n plus 1. No. Okay, I will automatically mark that wrong. The absolute values will kind of get rid of the negative terms. So if you were to list every term in this limit as you were investigating it, so an n is 1, n is 2, n is 3, n is 10, n is 1,000, because you're dealing with the absolute value of something, all of those terms, regardless if the term inside the absolute value is positive or negative, once you take the absolute value, it'll clean out the negatives. Okay? So you're not going to see negatives inside these absolute values anywhere in the universe. Nobody does that. It would be no. It would be a big no, a hard pass. Okay, so in your quiz, if you are only watching the video up to the point where I pause the video and you said, I'm not even going to give you a second chance. Okay, no. That indicates to me you're not watching the videos. You're just picking and choosing which parts to watch. So I should not see a -1 inside the limit, inside the absolute value there. The absolute values kill off all the -1 stuff, right? All right. Okay, so anyways, here I need rho to be less than 1. Okay, so we could kind of figure out this inequality by looking for the critical values, so to speak, the places where x squared minus 1 is actually equal to 0. That'll be at -1 and 1. And then you could do test values, signs, and conclusions. So test value x equals -3. 9 minus 1 is positive. Okay, so that is greater in that interval. X equals 0. That is negative, so that's the interval we want, I believe. And then like x equals 5, so that would be 25 minus 1 is positive, so it's greater. So the interval I want is from -1 to 1. Okay, so the radius of convergence in that case, again, the radius is only half the interval, so -1 to 1. So you're kind of thinking, okay, the radius is 1. Okay. All right, now I need to get the interval of convergence, and in order to do that, again, because the rho value would actually equal 1 at either -1 or 1, you need to investigate those endpoints. Okay, so you'll have to look at x equals -1, and plug -1 in wherever I see an x in the original power series. Okay. And then you simplify the heck out of that thing. What the heck is that? adding exponents to like bases, you'll have negative 1 to the 2n plus 1 plus n is 3n plus 1 all over 2n plus 1. I'm trying to get a handle on that thing. It's probably like a n plus 1 or n. What is negative 1 to the 3n plus 1? So that's negative 1 to the 3n times negative 1 to the 1 all over 2n plus 1. This thing right here is negative 1 cubed to the n value. Okay? So negative 1 cubed is negative 1, and then that's raised to the n. And then we can put it back together. Right? This is the sum negative 1 to the n plus 1 all over 2n plus 1. So it's just an alternating series, so you do your alternating series test. Try the AST. So tell me, the reader, which test you're going to do. The first step is to take the limit of the positive portion of the a sub, remember in the alternating series, we don't work with that negative 1 either. Just like here with the row value, I should not see a negative 1 in there. You should not see a negative 1 in this test. Anyways, we need two things to happen. We need that limit to be 0. We need the terms to be decreasing. So I'm going to look at a sub n plus 1 divided by a sub n. So it's going to be 2n plus 1 all over 2n plus 2 plus 1 is 2n plus 3. That's clearly less than 1, so hence this side is convergent. Okay. You need to show me that work. I've had millions of students on tests flip a coin, and no, that's not going to give me full credit. No, 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 no. Sorry, buddy. Plugging in 1 into the original series, I get negative 1 to the n times 1 to the 2n plus 1. 1 to any power is just 1, so I'm just going to replace that with a 1. And lo and behold, I got another alternating series. So I'll try the AST. And it's the same exact process, just duplicated. It's going to end up being 2n plus 1 all over 2n plus 3. That would be less than 1. So again, convergent. And so for our interval of convergence this time, if you have a convergent endpoint, you have to put a bracket. So I got a bracket on negative 1. And then likewise, 1 is convergent there, so I got to put a bracket over there. Okay? Okay, so that's the big and the small of it. Now what we're going to do is kind of work with integrating and differentiating these power series. This kind of happens sometimes in differential equations. You need to do power series representation for a function. You may not know what it is, and that'll come up in definitely in physics applications, like I think the Fresnel equations are of this type. I don't remember, to be honest. Is it Fresnel? Do you want to show me one? Apparently not. They're shy. It seems something about Fresnel's drum head modeling. Maybe that was it. Fresnel. No. Jesus, it could have been. Migrating drum head. Sorry, I'm going down a rabbit hole, I know. It's this thing. Fourier series, really? They use that? Because I'm not finding it. This is where they had to use power series for this thing. Okay, well, I don't know. Maybe it's in there somewhere. It's this thing, these basal functions. They're solutions of differential equations, and they should be in forms of power series. At least that's what I thought they were. Maybe I'm wrong. I don't know. Anyways, I guess it kind of looks like a power series. That's a Laguerre polynomial. That looks like a power series there. Okay, but they crop up. Okay, they crop up in some of these physics applications. That's a long story short, I guess. Oh, yes. Oh well. All right. So anyways, for us, you know, maybe not, we're not there at the physics level there yet, but for us, we're going to use differentiation and integration to kind of backdoor our way into power series representations for other functions. So it'll turn out we can pretty easily find a power series representation for some functions like 1 over 1 minus x, because this thing looks like just like a geometric, right? And that really is all that is. But if you were to integrate something like that, 1 over 1 minus x dx, of course you have to do a u sub on it. What do you get? You get negative ln absolute value 1 minus x. Okay, so if you integrate then this power series, you can get a power series representation for these natural log functions, which would be super cool, because we don't have really a need to do an approximation of 1 over 1 minus x, but we do have a need for doing approximations of ln's, right? The ln is not something that students typically can do in their heads. Think about it. What is the ln of 1.3? You know, you may be able to figure out the ln of things like e. The ln of e, I hope everybody knows, is 1. What is the ln of 1? The ln of 1 is 0. But the ln of 1.3, I don't know. So we're going to be able to get our hands on that via power series. But in order to get the hands on that particular power series, at least in the beginning, what we have to do are this kind of trickery. Okay, so we're essentially going to be integrating and differentiating power series. Okay, and that's what this next problem is all about, number 15. It is annoyingly long. So I will just warn you right off the bat. Anyways, number 15, here is our power series. And what I want to do when working in this context with derivatives and integrals, I usually want to kind of expand these things, because I'll kind of half and half it. Like, part of me will want to just take the derivative of the series, so you can literally just take the derivative of this expression here. The troublemaker, though, is this index, because if you're taking a derivative, think about it. If one of the terms is a constant, it will just turn into 0. So it'll change the series notation's index. It won't start at 1 anymore. It might start at 0. So I'm constantly kind of watching out for that effect by producing terms of the series, and it works kind of as a check. All right. So I'm gonna, n is 1, so negative 1 to the 1 plus 1 is negative 1 squared, which is positive 1. This should have an n on it. And then I have x minus 6 to the first power all over 1 times 6 to the 1. It'll alternate, and then this will be x minus 6 squared all over 2 times 6 squared. X minus 6 cubed all over 3 times 6 cubed, etc. I'll just put one more in there. Okay. I'm going to go ahead and get the derivative. So they want the first, second derivative, and then the integral of the thing. So for the first derivative, I'm going to cheat a little bit and take the derivative of this thing. Okay? So I'm taking the derivative with respect to x. So the only portion of it really that I have to take the derivative of is that thing in blue that I just circled. Okay? Everything else should kind of stay the same. And again, I got to watch out for that index, that n equals 1. Okay. Okay. But anyways, everything else is kind of in the pink. So I have n plus 1. I have to do a power rule, bring down the n times x minus 6 to the n minus 1 now, all over n, 6 to the n. I'm going to simplify that because I see, okay, there's a common factor of n in the numerator and denominator. So I'll have negative 1 to the n plus 1 times x minus 6 to the n minus 1 all over n 6. Well, that n is gone now. Okay, so just 6 to the n. You could then, check by taking the derivative of that series above. Okay, so what the terms of the f of x series, x minus 6 over 6, that's x over 6 minus 1. If I took the derivative of that, that would equal 1 over 6. So the first term of my series should be 1 over 6. So if I start at 1, is that going to work? Do I get 1 over 6 out? Plugging in 1, it'll be positive, and then you'll get x minus 6 to the 1 minus 1 is just x minus 6 to the 0, which is 1, and then all over 6 to the 1, so that first term works, right? And then you do d with dx of the next guy, x minus 6 squared all over 2 times 6 squared. That's going to be 2 times x minus 6 all over 2 times 6 squared, which of course is just x minus 6 all over 6 squared. So I got to make sure the second term in my series now is, and it should be negative, right, because this thing was negative. So plugging in, so this was n equals 1, plugging in n equals 2, I'm going to get a negative, that's good, x minus 6 to the first power all over 6 squared. And I think it's lining up, so I'm going to go ahead and just populate maybe one more term here so I can check it with my second derivative. So here is x minus 6, so it'll be now when n is 3 squared all over 6 cubed and then minus blah, blah, blah. Okay. For my next derivative, I need to take the derivative of these things, so I might as well go ahead and kind of do that. So this will be, the first term should be, well, it won't be anything, it'll just be 0. The next guy, it's negative x over 36 plus 1 6. So that next guy should be negative 1 over 36. And then the third one, do I dare? The third one, let me just take the derivative. So it's 2 times x minus 6 all over 6 cubed. Okay, so this is the first, n equals 1 in my next series. N equals 2, and then this dude was n equals 3. Okie dokie. So I need f double prime is what I'm after. So I'm taking the derivative of the guy above. And again, you need only take the derivative of the portion that has the x expression. So it's that portion right there. And let's not use that expression because that was not simplified. Let's use the one after it that was simplified. Okay, so I got negative 1 to the n plus 1 times n minus 1 times x minus 6 to the n minus 2 all over 6 to the n. And because I took a derivative, I'm probably thinking that I need to change this lower index to the number 2. Okay, that's my guess. Okay. So let's see if that's what I get. And I should get those blue numbers, right? All right, so if I plug in 2, I get negative 1 cubed, which is negative, times n minus 1, so again, this is n equals 2 here. So 2 minus 1 is just 1, and then x minus 6 to the 2 minus 2 is just 0, so x minus 6 to the 0 is 1, all over 6 squared. And that's it. That's n equals 2 from above. Okay, that's this guy right here. And then the next one should be this guy, so let's do n equals 3. So I get plus now. And that will be 2 times x minus 6 to the 3 minus 2 is just 1 all over 6 cubed. Yeah, and it looks like it's working. Let me get another one just for the records. The next guy, n equals 4. Should be negative 3 times x minus 6 squared all over 6 to the 4th plus da da da. Okie dokie. So there's that stuff. And once you get into, if you're doing sort of mathematical physics, you're probably going to want to get all of these indices the same. That way you can kind of combine all your summations into one summation. And to do that, it's basically, you could just say, all right, I want to replace n with n minus 1. Okay, so if you subtract 1 from both sides and then do a substitution for n minus 1, it should change the position of that series. And then if you had to, you could kind of combine these all together and you're into a differential equation, which you study later on. Okay, okay, but there's that. We still need the integral. Okay, so the integral guy, integral f of x dx, that will be the integral of that summation above. And again, I could kind of get my hands on it by just taking the integral of that blue portion, right? So it'll be the sum from n equals something to infinity. Again, I got to be a little careful about that lower index. -1 to the n plus 1 times x minus 6 to the add 1 to the old exponent and divide by it. N plus 1 times n times 6 to the n. Right? And what do I need that to be? So if I were to integrate these terms, what would I have? X minus 6 squared all over 2 times 6 minus x minus 6 cubed all over 3 times 2 times 6 squared plus blah, blah, blah. So I should get those red terms when I plug in the indices. So let's guess n equals 1. I think that well, you'll have to start at 0, right? N equals, because the first term, oh, I need a square on the first term, so n equals 1 will work. Okay. So yeah, I got -1 to the n, 1 plus 1. So this is for n equals 1. That is positive, and then you get x minus 6 squared all over 2 times 1 times 6 squared. And then the next guy will be minus x minus 6 for n equals 2. This will be cubed all over 3 times 2 times 6. Yeah, so it's definitely working. And then so on and so forth. We'll just leave it at that. Okay, great. So there's my series. Okay. For us, what we need to do is figure out their convergence, the intervals of convergence for these characters. So there's some goodness involved. You're not going to have to do like 4 different ratio tests. So the deal will be the radius of convergence will not change when you differentiate or integrate. Okay, that's great. The bummer part is that the radius will probably, the interval, the endpoints on the interval will probably change. And usually the deal is when you take the derivative, you'll maybe lose the endpoints, and when you integrate, you maybe gain the endpoints. Is kind of the pattern I've seen. But don't, I mean, you could use that pattern, but kind of don't abuse it. Okay. Okay. It'll probably get you through the homework, but in general, don't, if people's lives depend on it, please don't cut corners. So the radius of convergence will not change when you differentiate or integrate. Unfortunately, the endpoints of your interval may. There's a point where, okay, well, anyways, so what I do is kind of first get the radius from the original function. So first find the radius, and the original function, we've probably forgotten, the original power series was this guy. Oops. What the heck was it? X minus 6, there we go. And it's just to the n. All over and 6 to the n from n equals 1 to. Okay, so first find the radius using that. So rho be the limit of the absolute value of a sub n plus 1. And again, you're not going to include that negative 1. The absolute value will get rid of it. So I get x minus 6 to the n plus 1 all over n plus 1 times 6 to the n plus 1 times the reciprocal of all that, which will be 6 to the n times n, the reciprocal of a sub n, rather, all over x minus 6 to the n. Then you can use your rules of exponents to simplify. So I get the limit of x minus 6 to the n plus 1 minus n, which is just n to the first power, divided by 6 to the first power, and then we have this n all over n plus 1. I can factor out anything not dependent on n, so I'm going to move that x minus 6 out of the limit, and you have to keep the absolute values on the variable part, but we can kind of, the absolute value in the denominator of 6 is just 6, so I could rewrite that. And then the limit of n over n plus 1 is just 1. So we get the absolute value of x minus 6 all over 6. And the ratio test says that when that's less than 1, we have absolute convergence. So I'm going to rewrite that as that, and then add 6 to all three sides. And it looks like our radius of convergence is 6. Remember, you take half the interval. The question then becomes, what's happening at 0 and 12? Okay, and that's the trouble. Now you have to go through and check the endpoints for each individual function. Okay, so there's 4 of them. You're going to do 8 convergence tests, essentially. All right. So for this, what I kind of do is just kind of make a chart and blow through it. I'm not going to be exact on this. And of course, I won't put one like this on the homework, or on the test rather. This is a little too much work for a test problem. So I got to check at 0, and then I'm also going to be checking at x equals 12. And I'm going to do an abbreviated check. Please don't shortchange me on a test. I'm only doing abbreviated for the sake of my own sanity and for the sake of time. So I have the sum of here, -1 to the n plus 1, and maybe somewhere for reference, where the heck is the original function? This guy. I'm not going to make a chart after all. That guy's f of x. So anyways, plugging in 0, I'll get 0 minus 6 to the n, and then all over n, 6 to the n. That'll be, you could, so if you, so I got -1 to the n plus 1 times -6 to the n. -6 to the n is -1 times 6 to the n. So I got -1 to the n plus 1 times -1 to the n times 6 to the n. And then that will be -1 to the 2n plus 1. So -1 to the n plus 1 plus n is 2n plus 1 times 6 to the n. I'm going to bust that into -1 to the 2n times -1 to the 1 times 6 to the n. -1 to the 2n is the same as -1 squared to the n. It's -1 to the 1. -1 squared is +1. So you get +1 to the n times -1 times 6 to the n. In other words, you just get -6 to the n. So I have -6 to the n all over n, 6 to the n. You could cancel out the 6 to the n's, and you get -1 over n, which is a constant multiple of the harmonic. And then, of course, it's divergent. Okay. All right, let's do the other endpoint. So I have the sum -1 to the n plus 1 times 12 minus 6 is 6 to the n over n, 6 to the n. 6 to the n's cancel, and we have an alternating harmonic, right? So I have to do alternating series tests. So the limit of 1 over n is definitely 0. Then look at the ratio of consecutive terms. So a sub n plus 1 is 1 over n plus 1. A sub n is 1 over n. Reciprocate. That is definitely less than 1. So in this case, it converges by the AST. Okay. So the interval of convergence for f of x, I'll just put it up here. Oh, I guess I don't have the room here. The interval of convergence, so we had divergent at 0, convergent at 12. Okay, okay, let's get our next critter, f prime. I'm going to borrow. Okay, so this time I have f prime of x. And same sort of spiel. I need to check x is 0. And then check x is 12. So first plugging in 0, I get the series -1 to the n plus 1 times -6 to the n minus 1 all over 6 to the n. Okay. We could split that -6 up into -1 times 6. And that's what I was kind of doing up here in this work. Okay. So back over here and all that jazz. I'll write it out in case you need to see it again. So -6 to the n minus 1 is -1 times 6 to the n minus 1 is -1 to the n minus 1 times 6 to the n minus 1. And then, you know, there's that -1 to the n plus 1 in front. So that's a like base with the other -1. So you get -1 to the n plus 1 times -1 to the n minus 1 is going to be -1 to the n plus 1 plus n minus 1, which is 2n. 6 to the n minus 1 over 6 to the n. -1 to the 2n is just +1. So we'll have 6 to the n minus 1 over 6 to the n, which is 1 over 6. And then, seems like I made a mistake with that. Well, anyways, the nth term test, do the nth term test for divergence. The limit of 1 all over 6 is equal to 1 over 6, which is not 0, and that implies it's divergent at that endpoint. Okay. Okay, so try 12. So I get the sum -1 to the n plus 1 times 6 to the n minus 1 all over 6 to the n. This will just be alternating then. So it'll be the series -1 to the n plus 1 all over 6. 6 to the n minus parentheses n minus 1 is the same as 6 to the n minus n plus 1, which will just give you 6. And then you do the nth term test, right? So, sorry, alternating series test. So this time I start with the limit of 1, 1/6, right, which is not 0. So we're going to say that's divergent. You technically need the nth term test for divergence, but I'm allowing you to just stop it at that point and say divergent. So here, when you took the derivative, and this is, in my experience, what typically happens, you lose an endpoint of convergence. So 0 is still divergent, but then 12 also will become divergent. Okay, so it goes from convergent to divergent. Okay, second derivative now. Well, again, I'm going to copy and paste this critter. Crap. Oh, of course. I didn't touch anything. Second derivative. I wonder if I could just copy that. Why even bother? Screw it up somehow. Wait, this guy's f double prime. Again, I'm checking the endpoints x equals 0 and then x equals 12. When x is 0, I get the sum -1 to the n plus 1 times n minus 1 times -6 to the n minus 2 all over 6 to the n. So again, I want to get rid of this -6 to the n minus 2 and kind of, you know. So what do we got? -1 to the n plus 1. And if you split the -6 to the n minus 2 up into pieces, it's -1 to the n minus 2 times 6 to the n minus 2, right? So this will be -1 to the n plus 1 plus n minus 2, which is 2n minus 1 times 6 to the n minus 2. So -1 to the 2n times -1 to the -1 times 6 to the n minus 2. -1 to the 2n, of course, is -1 squared to the n. -1 squared is +1. So you have 1 to the n, which is just n, or sorry, it's just 1. And then -1 to the -1 is -1. It's just 1 over -1, which is -1. And then you have the 6 to the n minus 2. Okay, great. So I have the sum of n minus 1 times, there's a negative floating about here, so let's put that in front. And then 6 to the n minus 2 all over 6 to the n. So exponent rules again. The sum -n minus 1 all over 6 to the n minus n plus 2, which is 6 squared. And then you can do the nth term test. That's going to be divergent all over the place. So the limit of -n plus 1 all over 36 is going to be -infinity, which is not 0. In other words, it's divergent. And then the other guy, I have -1 to the n plus 1 times n minus 1 times 6 to the n minus 2 all over 6 to the n. That will be an alternating chi. So -1 to the n plus 1 times n minus 1 all over 6 squared. And do alternating series test. So step 1, I have the limit of n minus 1 all over 6 squared, which is infinity. So we're going to say it's divergent automatically. Okay, so again, we have divergence at the endpoints. And our interval of convergence is just 0 to 12. Okay, last but not least, we have an integral. And like I was saying, usually when you do an integral, you're going to end up gaining an endpoint. So if my stupid thing would work, it's so desperate not to allow me to do this process. You know. Jeez. It's like the computer is actively working against me. Like AI, the singularity has already started, and it's the code is actually trying to make my life worse. You know, anything that I do, it learns to make it more difficult. All right. I don't know why. The integral of, you know, that's the singularity. If you don't know what that is, look it up. AI is taking over. Okay. Right. So this time you want to look at the integral. X is 0, x is 12 are our endpoints again. Plugging in 0, I have the sum -1 to the n plus 1 times -6 to the n plus 1 divided by n plus 1 times n times 6 to the n. Okay, so again, I'm going to split that -1 off. So it would be -1 to the n plus 1 times -1 to the n plus 1 times 6 to the n plus 1. That'll be -1 to the 2n plus 2 times 6 to the n plus 1. That will equal -1 squared to the n plus 1 times 6 to the n plus 1. And -1 squared is +1. 1 to the any power is just 1, so that part kind of goes away, and you just have 6 to the n plus 1 all over n plus 1 times n to the times 6 to the n. That will be the sum of 6 all over n plus 1 times n. That's a telescoper, if I've ever seen one. We might as well do a telescoping just for the sake of memories. So I have a PDF of 6 all over n plus 1. I don't even know where it started. N equals, is it 1? 1 to infinity. N plus 1 times n. That will equal a all over n plus b all over n plus 1. Multiply through, you get 6 equals a times n plus 1 plus b times n. That n is negative 1, so I have 6 equals negative b, so b is negative 6, and then n equals 0, so a will be 6. So this will be the limit of the sum of 6 all over n minus 6 all over n plus 1. Then you expand it, so this will equal the limit of the sum of, let's see, 6 over 1 minus 6 all over 2 plus 6 over 2 minus 6 over 3 plus 6 over 3 minus 6 over 4 plus blah, 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 plus, and then we want the last 3 terms. The last term, let's say it's going to k, so n equals 1 to k, and then we're taking the limit as k goes to infinity. Okay, so what do we have? The last term, I said k, so 6 all over k minus 6 all over k plus 1, so this is n equals k. Then the one before it is n equals k minus 1. So I have 6 over k minus 1 minus 6 all over k, and the one before that, n equals k minus 2. So I have 6 all over k minus 2 minus 6 all over k minus 1, and then the cancellation is pretty obvious. So the term before it is canceling with this guy, this is canceling with this guy, this is canceling with this guy, and we're ending up with the limit of 6 minus, this guy's gone, 6 over k plus 1 as k goes to infinity, that will equal 6. It's definitely convergent. Okay, long story short, convergent. We even know what it adds up to. Okay, well that was an interesting journey. Negative 1 to the n plus 1 times 12 minus 6, so 6 to the n plus 1 all over n plus 1 times n times 6 to the n, so this will be the sum. Negative 1 to the n plus 1 times 6 all over n plus 1 times n, that's alternating, AST. So first show that the limit of the a sub n portion is going to 0, that most certainly is. And then secondly, show the terms are decreasing. So a sub n plus 1 is n 1 over n plus 2 times n plus 1 all over 1 all over n plus 1 times n, that's a sub n. Reciprocating, this will be n times n plus 1. I don't know if reciprocating is really a math word, so please don't go around saying that. I'm just saying it for the fact that my English is not all that great. Even though I am a native speaker, it's embarrassing, but anyways, this is less than 1, I think clearly, so hence it is convergent. Congratulations if you made it to the end. The IOC, the interval of convergence, is going to be from 0 to 12, and it picked up convergence on the endpoint 0. Okay? So I think for the homework, if you don't care about math and you're just trying to get your pharmacy degree or something, you could probably get the radius and just use, and then you probably have to get the radius convergence for the original function And then use this idea that if I differentiate, I lose convergence, and if I integrate, I gain convergence in order to pick and choose out the answers for 9.8. The last two problems are, the last two problems are just like this. So you can kind of get the interval for the first one and then use derivative, lose convergence, integral, gain convergence for the intervals. Okay? And that'll make your life a lot easier unless you want to become a math teacher for calculus, and then you should be able to kind of, if I can do it, you should be able to do it kind of idea. Okay, thank you for watching as usual, and I'll see you next time.